All right, guys. So we're going to begin our unit on, or our lesson, excuse me, on specific forces. I believe this is video 2.3. The first slide here is really just the forces that are in everyday common situations. So the first one we'll talk about is weight. Or another word or idea that is equal to weight is the force of gravity. So it's attraction between two masses. We represent that with Fg. So F for force, and then the letter or symbol for what it represents, which is big G for gravity. Normal force is a force that we'll talk about. That's a force between two surfaces, or a surface and an object that's touching it. And that's F sub n. So again, F for force and n being the normal force. Friction, which is a force between surfaces, sort of rubbing or touching. Again, it's contact force. And that is F sub F. And then finally, tension, which is the force between two objects that are attached to a string or through a string or a rope or cord, and that's F sub T. So those are the common ones that we'll have in a lot of different situations. There are sometimes other ones like applied forces, which is just somebody's pushing or pulling, and you can just label them force push, force pull, force apply. It doesn't really matter. But these are really common ones that come up a lot, and they have some characteristics that we're going to discuss. So the first thing we're going to talk about is the difference between mass and weight, because they are two different concepts. So you guys probably are familiar with the term of mass somewhere if you took chemistry class, and you already have a familiar everyday kind of common use of the word weight. It's kind of like how heavy you are. And there is a relationship between mass and weight, but they are not the same thing. Okay, so going through the definitions, mass is in chemistry is defined as the amount of stuff that makes up an object, the amount of substance or matter. Physics defines mass as the amount of inertia that an object has. So we talked about inertia with Newton's laws, and that's the resistance to any change in motion. So the more massive something is, the more inertia it has, and the harder it is to get it to change its state of motion. So the harder it is to get it to start moving or to stop moving or to change how it's moving. So that's the way we more look at it. But it kind of makes sense. Like if you have an object that has more matter within it, it's going to be harder to get it to move. That idea makes sense with inertia. So weight is not the same as mass. So weight is defined as the force of gravity that is the attraction between two masses. So if you think about our weight that we focus on is primarily based upon our attraction to the Earth. So I'm going to draw a circle here in blue, or close to a circle, and I'm going to write E in there. So that's supposed to be the Earth. And our body, which might be this red stick figure, which is really big because we're not really that big compared to the Earth, obviously, is attracted to the Earth. So there's some force trying to pull the center of our mass, or where our mass is mostly average location is, that's pulling it towards the center of the average location of the Earth, which is the center. So in our definition, or our equation for gravity, it's Fg equals mg. M is the mass of that object, so that's the object that is being pulled towards the Earth. And then lowercase g is the acceleration due to gravity, the same 9.8 number that we have used in our kinematics lessons and projectile motion lessons. So 9.8 meters per second squared. And we said this is the acceleration due to gravity, and that is directed downward. So in our frame of reference, most of the time we think of us standing on a flat surface, even though the Earth is technically round. But that idea is pulling down. So that attraction, if we drop something, it falls downward in our frame of reference. So we're not always standing at the top of the Earth, but we could stand, if you're in Australia, you're visiting Australia. If you're down here, and I cut off the person's head, but the force of gravity would be pulling kind of towards the center of the Earth. But for our everyday common problems, we just kind of draw this arrow down. If you want to put in the negative here, that's okay. The negative means down, and that would always kind of put our direction for gravity in that downward direction. So that's okay. So that's one difference between them. We're also going to talk about normal force, and then we'll kind of talk about the normal force and how the gravity force and normal force are influencing each other lots of times. So the normal force is a force that keeps one object from penetrating into another. So anytime two objects touch, so if you touched the computer key to go to the next slide or something, you're pressing on it, that contact, there is a normal force. So your finger isn't like magically going through the keyboard key, it presses against it, and the keyboard key presses back. So it's a force that stops things from penetrating through or flying through one another. The normal force is always perpendicular to the surface. So the perpendicular symbol in math class looks like an upside down T, and that means 90 degrees. So 90 degrees from the surface is where the normal force acts. So lots of times we'll have horizontal surfaces. So if we're talking about like a flat floor, and we're going to put maybe a box on that floor, so I'll draw a box. And we'll talk through these situations in a little bit. The normal force is what is keeping the box from falling through the surface. That's essentially what it is, and it acts perpendicular to the surface. So the surface is horizontal, then the normal force would be pushing in that upward direction in this case. But your floor isn't always horizontal. You don't always have a flat surface. So when that changes, so does the direction of the normal force. So a lot of people think the normal force is always directed upward, and it is not. Okay. There is no formal equation to calculate normal force. So in the gravity equation, it was Fg equals mg. In normal force, you have to figure it out from using vector math and understanding the other forces that are acting. So the normal force kind of balances the forces in the direction of the normal force. So it makes it so that there is no acceleration in that direction. And we'll see this here in this example that I'm about to do. Okay. So it says if the box has a mass of 5 kilograms, we want to find the weight or the force of gravity. And then we want to figure out what's the normal force acting on the box. So how much is the floor or table or surface pushing up. And then we're going to adjust that and change it a little bit in these other cases down here at the end. So for the first one here, let's find the weight of the box, so the equation for Fg. Just writing it out. So you can write a capital G or a lowercase g. It doesn't really matter here. That's supposed to be G. Let me type it. That'll work better. All right. So Fg equals mg, and we're going to plug in the numbers. So if we do that, let me move this so I don't run out of space. There we go, and delete all that. So m is 5 according to this problem. It's supposed to be a 5. It's not writing. Try again. There we go. Nope. Okay. Equals 5 times 9.8. 9.8 is that accelerate. 9.8 is the acceleration of your gravity. That's going to get you 49 newtons. So sorry, this is being technically difficult. There we go. Equals 49 newtons. Sorry about that. That was really difficult to type. So 49 newtons is just 5 times 9.8. Where is it directed? It's directed down. So that's what you do. So I'm going to draw a free body diagram here. So we've done this before. So if we draw a dot to represent the object, undo that and get a better dot. So there's the dot. If I draw gravity going down, so gravity is Fg. And we just figured out that number, that Fg is 49 newtons, and it's directed in that downward direction. We need to figure out how much does the normal force push up. So the normal force is pushing up, and if we think about the box itself, what is the box doing? The box is just sitting there, right? So it's not accelerating, it's not doing anything. So while that's happening, that has to be the situation. The forces have to make that situation happen. So I would say that our box is not accelerating, so the net force is 0. So that means that our forces have to be balanced. So the force going down has to be canceled out by some force moving up, or trying to push up. So that force pushing up is the normal force. So this normal force is going to push up. So I got an arrow going up here. And that amount going down and that amount going up should be the same. So this normal force, if I write it out as Fn, should be equal to 49 newtons. If it wasn't equal to 49 newtons, what would happen? Let's think about that. So we have 49 going up and 49 going down. They just balance out. It doesn't accelerate, so it's going to do whatever it was doing. Our box was originally at rest, so it's just sitting there. It's going to stay sitting there. If the normal force was larger than 49, what would happen to the box? It would start accelerating upward. So like the surface isn't throwing the box upward. That's not true. So it's not going to make it jump off the table. Also, the table is like the normal force isn't weaker than the force of gravity. Otherwise, it would fall through the table. So both of those situations can't happen, or they're not happening in this case. So we have the normal force and the gravity force are balanced. They are not always balanced. So I'm going to go through some examples where they are not the same thing. All right. So in this next one here, so we did the first two dots or things. So we're on to this third one. It says, if I push downward on the box with an 11 Newton force, or 11 newtons of force, what is the normal force then? So this is just to show you that the normal force adjusts and changes however it needs to. So if I have the force of gravity, it's still the same box. It still has the same mass, same 9.8 for the acceleration due to gravity. So we still have 49 going down. But now I'm going to add another arrow going down. That's 11 newtons. And I'm just going to write in 11 newtons here. That would be the force from me, or the applied force, or the pushing force, however you want to label it. I'll label it FP for push. Okay. So we got a pushing force is equal to 11 going down. We have a gravity force, which is 49 going down. So if we look at all the downward forces, we have, it looks like 60 newtons going down, because 11 plus 49 is 60. Now, if the normal force didn't change, what would happen? The gravity and pushing force would make the box fall through the ground, and that doesn't happen either. So normal force has to adjust. So this arrow here that I'm erasing for the normal force is going to get larger. So it's going to get larger in a way so that it will cancel the two forces that are going down outward. So I have like now this arrow going up. That is the sum of those two. So if I had 60 newtons total going down, the new normal force, so Fn, would be 60 newtons going up. So okay, hopefully this is making sense. We got one more example just to try to drive this idea home with the normal force. So in that case, in this third one here, it would be 60, because 60 going up and 60 going down would make the situation work. And the last one here, if I pull on the box with 11 newtons of force, what's going to happen to the normal force? So let me pause a second. Sorry, I just sneezed, so I paused so I didn't make a huge noise in their microphone. So so if this new situation is we're trying to figure out what is going to happen to the normal force if we take this pushing or pulling force and I make it go up. So so again, we still have 49 going down. So the gravity force hasn't changed because m hasn't changed and the acceleration due to gravity hasn't changed. So this is a constant value. But now we're applying a force going up. So if I apply a force going up, I'm kind of taking away some of the force that the normal force has to supply. So if I I was trying to shrink the arrow. So if I shrink this arrow down, these two forces going up, that black arrow here and this red arrow, which is the pull or the applied force, so FP, for a pulling or pushing force, whatever force it could be, that's equal to 11. So the normal force, which is that arrow that I adjusted, that I'm not drawing in, the one that looks better, that is going to balance out the situation. So if I have a 49 going down and 11 going up, I have an extra 38 going down. So the normal force, which is this black arrow here on the left side, that is going to cancel that out, the 38 down, because it's going to make it so that it's balanced. If I somehow applied an exact amount of force to hold something up, so say like I was holding this box in the air, or if I just was holding it right above the ground, so 49 is still going to go down, I would be holding 49 going up, or applying a force 49 going up. So they're going to cancel out. And then the normal force would be 0. So the normal force just adjusts. The normal force can't be negative, though. It's not like sucking things into the surface. So that's not how it works. So the normal force is always applied in a direction that's perpendicular to the surface, and it's always going to try to make the forces in that perpendicular direction cancel out or be balanced. Sometimes normal force is associated with with the force of gravity at all. So if this was like a book that I had next to a wall, and I wasn't holding it, I would just let go and it would fall straight down. And this gravity force has nothing to do with the normal force. If I started pressing the green book against the wall, so that was supposed to be a G, sorry about my, and so if I took my hand and I applied a force going kind of in towards the wall, so that arrow pushing in, if that's the applied force or the pushing force or the person force, the normal force would have to counteract that to keep it from the box moving horizontally. So if that was going to the left, or I'm sorry, to the right, this one would have to go to the left, and that normal force is unrelated to the gravity. So if I pushed really hard with this force going to the right, if that force got really big, this normal force would have to get really big. If I just pushed a little bit, the normal force would just push a little bit. So it's just it's all related to that. Now, if this was the case, the box would start sliding down, and that is not what would happen if you held a book against the wall, because there'd be another force that would be going up, and that's the next force that we're going to learn. So this force going up would cancel out this gravity force, so they would be equal in size, and that force is actually going to be the next force that we learn, which is the force of friction. Okay, so the force of friction is that one. So before we get to the force of friction, though, you could also have normal force on a ramp. So if the surface is going slanted, again, perpendicular to surface is the way that the normal force goes. We'll, in another lesson or two, talk about that situation in more detail because it's a little mathematically tricky. Okay. So let's just practice a little bit. We're going to practice a couple of cases and try to identify the forces acting and which way they would go. And then we'll go through one example problem, and then I'll get into normal force, friction and tension, which tension goes really quick, but friction is related to normal force. Okay, so this ball at the top of the ramp is going to roll down, and we're going to ignore air resistance. We want to know what is the force on what force or forces act on the ball as it moves through the air just after leaving the ramp. So if it flies off the ramp, the ball's somewhere over here in the air where I make the green dot happen. We're talking about the forces there. So can you imagine the forces acting and try to figure those out? So we've only talked about a couple forces so far. But forces are just things that are pushing or pulling. So think about the things that are pushing or pulling on this ball. So I would say that there is a weight force trying to pull down, the force of gravity. That's going to be present the whole time. So that's there. Is there anything else? So is there anything pushing it right or left? I don't think so. We've ignored air resistance. We're not. It's not attached to like a jet or something. There's nothing pushing up. So I think gravity is the only force acting. That's it. That's the only one. Because it's not in contact with anything else. So weight is the only force that, or gravity is the only force that we're worried about. Okay. Let's do a different one with the, let me go back because I wanted to talk about this part. How about when it's on the ramp? So when it's on the ramp, are there other forces acting on it? Yeah, it's in contact with some stuff. So we still have gravity. Gravity's still trying to go straight down. And even though I didn't draw that arrow straight down, you get the idea. That's gravity. There is a normal force acting on this. So the ramp is pushing, like it's not falling through the ramp. So the normal force, we just did a quick note on that. So that's going up and to the right there, it looks like. And there might be friction. It didn't say the ramp was frictionless. So the ramp would go up that way. Friction on the ramp, because friction, which we'll learn soon, and you probably already know, opposes motion. So if the ball is rolling down the ramp or kind of in this direction that I'm drawing a red arrow, if that's the velocity of the ball or the intended velocity of the ball, then the friction force is going to go against that and try to keep it from moving or slow it down as it moves. So that was just a different part of that example problem, which I think is good. Okay. All right, so we're going to try this problem together, and this is sort of a preview for the next types of problems that we're going to get into. The next video, we do some problem solving, and we tie in all these things, but it's all really the same process the whole time. You're going to draw a picture, you're going to set up your table, you're going to fill in the forces, you're going to decide the directions. If you have to do trig because stuff's at an angle, you're going to do trig. This one has an angle, so that means we got to do trig. And then you're going to sum up your columns or solve for the missing box in the columns and figure out anything else that it asks for, like an acceleration using maybe Newton's second law. So So it says a gardener mows a lawn with an old-fashioned push mower. The handle of the mower makes an angle of 32 degrees with the surface of the lawn. So they're kind of pushing. So I would imagine if this is the lawnmower, this red dot, I would imagine this force is going down and to the right. And I didn't draw that exactly great, but it's fine. I'll say FP for F push. Okay. And it's at an angle. So it's not right, left, up, down. So that's at some angle. So I'll draw a horizontal line here just to make sure that you can imagine, okay, it's going at some angle with the surface below, kind of you're pushing along the handle. It says if the 249 Newton force is applied along that handle of the 21 kilogram mower. So 249 newtons, that's how much we're pushing, that's FP. 21 kilograms, that's the mass. So I'm going to write M for that. That is not a force. Remember, mass is not a force. It's related to gravity. So we're going to use it to calculate the force of gravity, but it's not the force of gravity. It says what's the normal force exerted on the mower, and then what's the acceleration. So again, drawing our free body diagram, we got this force going down to the right. We also have gravity. So for the force of gravity, that is going to be how much the earth is pulling on the lawnmower. So I'm going to draw an arrow. And again, I was trying to make that go straight, but my mouse pad is not tracking that way. So I'm going to call that FG. It doesn't say there's friction, so we're going to ignore it. We're going to assume there isn't any friction, even though there would be. We haven't learned the part about friction yet, so you can't really deal with that yet. But there is a normal force. So if you imagine the surface is a horizontal surface, and that's what we would expect unless it specified something else. We got gravity going down. We got pulling force or pushing force down and to the right. So we're going to have a normal force going up. And my indication would, or my inclination would be to believe that this normal force, which I had perpendicular surface going towards the top of the page, is larger than the gravity force. Because if they were just balanced, that would be fine, but we're pushing down on the lawnmower too. So we're pushing down and to the right. So the normal force is going to have to kind of cancel out both the forces going down. So step one, this is our free body diagram. We did that in other videos too, so hopefully that's starting to make sense. So free body diagram, excuse me. Then I'm going to set up my table. And the table really does most of the work for you. So if I set up this table properly and I fill in the numbers, it will lead me to what I need to do mathematically to solve. Okay. So I'm going to set up a chart. And I'm going to list the three forces that are in my free body diagram. So all the forces that are in my picture, I put over here. So Fg for the gravity, Fp for the pushing force. That one's going to be the trickiest one to calculate, I think. And then Fn. Those are the only three arrows. That's the only three forces I have. And then when I add them all together, I get the overall outcome or the net force. So this is going to be F net. And then at the top of the two columns that are empty right now, I'm going to have the different directions. So I have the X direction, which is the horizontal, and I have the Y direction, which is the vertical. So again, Y direction is going left to right. I'm sorry, I screwed that up. Y direction, X direction is left to right. It's going across. And we know positive is right and negative is left. And then for the Y direction, before I misspoke, the Y direction should be going up and down. So that is the up and down direction. So up is positive and down is negative. So we're going to try to fill in some numbers and figure out things, and we might have to use an equation or formula too. That's okay. But before I get into any numbers, I just want to figure out which way things are headed. So because this directional aspect of these forces is equally as important as to getting the numbers right. So if you don't kind of understand the direction in which the force goes, when you try to add it to another force, it's not going to work out right. So let's just go through these three forces and decide which way they're going. So gravity, it looks like is pointing straight down, so it's not going left or right. So that's going to be 0. And gravity is moving towards the bottom of the page or pointing towards the bottom of the page. That's the negative Y. So I have a negative there. For the pushing force, it's going, it looks like right because it's going down and right. So that's going to be right, which is positive. That's the X. And down is still negative because it's still towards the bottom of the page. Finally, the normal force is the one that's going up, so it's positive in the Y, and it's not going left or right, so that's going to be 0 in the X. So we filled in 2 zeros, and we filled in all the positives, negatives, and zeros. And if you think about this lawnmower, does the lawnmower accelerate? And this is the question you should ask yourself. Does the object accelerate in any direction? So I think the object is going to definitely accelerate to the right. So I would expect this to be positive for the net force, but I'm going to let the math show me that it is. And I only have one force, and it's positive, so it's going to be positive. Whatever that pushing force in the x is going to be my net force in the x. And then in the y direction, it shouldn't accelerate. So if you imagine a lawnmower, if I'm pushing a lawnmower across my yard, it doesn't shoot up off the surface or fall through the surface. So that's going to be 0 here. Okay, so those are some like tricks. This happens a lot where the y direction cancels out and goes to 0. So we just need to fill in the other number. So we're going to have to do some math. So for the gravity equation, and I'll try to type to make it nicer again, because that will be, I think, appreciated. So for the gravity force, it's just using the gravity equation. So it's Fg equals mg. So m was 21, and then g was 9.8. We're going to multiply them out. So 21 times 9.8, when you do that in your calculator, you get something really close to 206. So 206 newtons. So I'm going to write 206 up there. Oh man, my handwriting is really bad in this video. I apologize. 206. And all these forces in here are newtons. So you could write n in all the boxes, but we're just at the bottom. It's fine. That'll be newtons. That'll be newtons. Okay. So 206 newtons, that's our force of gravity. For the normal force, there is no equation. So I'm going to have to use kind of the other forces to figure this one out. So that's going to be the box that's missing here. The pushing force I can do. I can figure out the pushing force because I have the size and the direction of it. So I just have to do some tricks. So I'm going to come back down here and type some more. So I want to figure out the pushing force in the x direction. And the pushing force in the x direction would be the pushing force, so Fp, times the cosine of the angle. So Fp, it said, was 249, because there's a 249 Newton force. And you're going to multiply that by the cosine of the angle that it's applied at. And it says, previously up here, it said the angle was 32 degrees. So that's going to be that. You're going to put that in your calculator, and it's going to tell you something like 211.2 is the value for that one. And it would still be newtons because it's a force. Similar work for the y. That's equal to Fp sine of the angle. So again, it's basically the same thing. You're just switching out the sine or cosine for sine in this one. And that's going to be like 132. Again, I rounded slightly just to make the numbers a little bit easier, but that's fine. I could have just made this 211. It doesn't make a difference, really. So I'm going to take those numbers and put them in the boxes. So this one's 211.2. And then over here, this is 132. We already put in the positives or negatives, which should match up with the way that the force is directed. So this pushing force is going down and right. So right is positive and down is negative. So we have all the boxes filled in except for one in each column. So if you look at this table, we have all the stuff filled in. So now we can just do the math. So 0 plus 0 plus 211.2 is 211.2. So 211.2 is the net force acting on this lawnmower. It's a pretty big force, but doable by a person. The other forces, the 206 and 132, we add them to some normal force and we get 0. So these two together, if I put them together, would get me 338 in the negative direction. So that's a 3 and a 3 and an 8. And that would be going down. But when I add the normal force to it, it goes to 0. So these two together are canceled out by the normal force. So this normal force is 338 newtons. And it's directed up because these two were directed down, so the normal force has to cancel it out. So that's it for the normal force. We figured out what is the normal force. The last thing is the acceleration. So this is using Newton's second law. So I'll again type this out to make it a little bit easier. So with Newton's second law, it says F net equals ma. So let me shrink this a little bit too. So we're going to plug into that equation. Our net force is 211.2. We already know our mass because that was 21. So it's 211.2 equals 21 times A. And we get to solve for A. So it'll be 211.2 divided by 21, which is equal to, I got 10.05. Whoops. 05. It'd be meters per second, or meters per second squared. Oops. Trying to make this fit and it's not being cooperative. There we go. That'll work. So that is our acceleration. And if I asked you which way the acceleration was going, it's going in the direction of the net force. The net force is in the positive x, and that's it. So this would be to the right. There we go. And that's like a problem that you use the free body diagram, you use your chart, you've used some numbers, but it's kind of bringing it all together. Okay. Couple more ideas. We'll get to friction and tension, and then I'll stop this video because it's going to get long. So friction, you are probably familiar with, is a force that opposes motion. So there are actually two different types of friction. There's something called kinetic friction, and there's something called static friction. And the word kinetic, if you're familiar with kinetic energy, means motion. So it's motion friction. So if something's sliding, then it's the friction that slows something down as it's moving or sliding. Static friction, the word static means stationary, so it's holding an object at rest, so it prevents the object from moving. For the same surfaces in contact, static friction is always going to be a larger force than kinetic friction, and that means that it's harder to get something to start moving than to keep it moving. Going through friction, both of the friction equations, both types of friction use the same equation, so it's FF equals mu Fn. This letter looks like a cursive U. It's the Greek letter mu, mu, and it is a coefficient of friction, which is basically just describing how slippery the surfaces are. So the lower that value, the more slippery the surfaces are. The higher the value, the rougher the surfaces are. Okay. Static friction, the other part of the equation here is Fn. That's our normal force. So the normal force it's directly related to the friction force. So the friction force depends on the normal force. So it matters how much the surface and the object are kind of squished together. So if you think about this example, and I try to do this, if you take your knuckles, like two fists, and put your knuckles together and try to like rub them against each other, they'll be bumpy, and they rub against each other, but it's bumpy, right? Take your two fists and then press them hard against each other. So like push against them hard and then try to move them. And you'll have a lot more difficulty in that because they're kind of locked in, right? So those knuckles get into a groove and it's harder to move out of the groove. That is what the normal force is doing. So if your normal force gets big, the two surfaces are kind of, the surfaces aren't exactly flat at a microscopic level. They're very bumpy. So those bumps and like imperfections, the bumps and the lows, they kind of get stuck in each other and it makes it harder to move. So that's how normal force influences friction. Static friction is a little bit different than kinetic friction because it has a limit. So static friction is basically the amount of friction you can provide to hold something in place. And it only does as much as it has to. That's what I mean by lazy force. So it only does as much as it has to, but it has a limit. So like, let me give you a quick example here, and I think this will go okay. So let me take a box. All right, so let's say there's this box on the floor. Okay. And the box is at rest, right? So if I drew the forces, I'd have a gravity force going down, right? That's going to be there. That's Fg. I'd have a normal force going up. That's going up there. They're canceling each other out because there is no acceleration up or down. The gravity and the normal force are balanced. And there are no horizontal forces. So this thing is going to be at rest. The acceleration is at 0. The net force is at 0. It is balanced. Everything's balanced. Now, let's say I try to start pushing this object. So I'm just going to push a real little bit, like a really small arrow, okay? So, and let's say I don't push it enough so it starts moving. So this red arrow is the push. So if I push just a little bit, in order to keep it balanced, I didn't affect the up and down at all. In order to keep it balanced, this gravity is going to have to push the opposite way with the same amount. So you can see everything's kind of balancing out still. So this friction, which is the force of friction, so FF for force friction, lowercase f. And then if it's not moving, you write a little subscript for static. So it would be S for static, so FFS. So the static friction force and the pushing force are essentially just canceling each other out in this case. So let's say, okay, I'm really trying to start it to move. So I'm going to take this pushing force and I'm going to push a little bit more. So I'm going to make it get bigger. So I'm going to make it get bigger. And let's say the static, and let's make up a number, so it's 2. So I push with 2 newtons. And let's say the friction force is strong enough to hold it. So friction it has enough friction that it's not going to move. So this green arrow, what's going to happen to the green arrow? It's going to get bigger. And how big does this static arrow get? It has to get the same amount as the applied force. So this applied force in red going to the right is going to get canceled out by the friction force going to the left, and that's 2 newtons. Now, eventually, you're going to be able to overcome that static friction force if you are strong enough. So let's say the maximum friction that can have is 3. All right, so let's say, but it's not always going to push at 3, because if this was pushing at 3 right now, if the friction force was 3 and the normal force was 2, or not, I'm sorry, the pushing force was 2, then it would start sliding backwards, and it would start moving without me pushing it. So that's not right. So the static friction just keeps adjusting to make it work. Okay. So if I pushed with 3, the friction would push with 3 back, and it would cancel, and it would stay stationary. But if I pushed with like just a little bit more than 3, so let's say I just pushed with 3.1. So my pushing force is 3.1. The friction force could hold up until I pushed with 3. As soon as I pushed with 3.1, that static friction force is gone. It's no longer static friction. It's going to change into the other type, which is kinetic friction, because it's going to start to move. Kinetic friction is easier to calculate. It's just one number. It's constant no matter what. So you just do the coefficient for kinetic friction times the normal force. The static and kinetic coefficients, this U value changes. So you will get those out of a chart, or they're going to be described in a problem, and you can figure it out that way. Okay. Last type of force we're going to talk about is tension. Tension is just the pulling force in a rope or cord or string, and it's just like an applied force. It's just through a rope. Okay. Let's go ahead and do one more example or two, and then just see how you guys learn that. So it says a steel beam hangs from a cable as a crane lifts the beam. What forces act on the beam? So we got our beam here. That's our object, and we're drawing a dot. And what are the forces acting? So, okay, there's gravity, because gravity is still present all the time. As long as you're on the surface of the earth, you're going to deal with gravity. What force is lifting the beam? So we got gravity and all these. Is it a tension force? Is it a force of motion? Is it a tension and force of motion? It's just the tension. Okay, so the tension force is the force in the cord or the rope, so the cable. Right now I have them pretty close to equal. If they were equal and it was moving, then it would be moving at a constant. That's not what I want. There we go. So Ft. If they were, if it was accelerating upward, you'd have to have a bigger force going up. So the tension would be larger than gravity force. Again, it's that tug of war mentality. Whoever wins the tug of war is the way it's going to accelerate. All right. So it's just, there is no such thing as a force of motion. Like, there's laws of motion, but there's no force of motion. All right, let's try one more, and then we'll stop. A bobsledder pushes her sled across a horizontal snow to get into it going. So like if you imagine a bobsled, she's going to push and jump in. After she jumps in the sled gradually slows to a halt. Now, what forces act on the sled after she jumped in? Okay, so if this dot represents the bobsled, what forces do we have? So do we have gravity? Yeah, we got gravity. Gravity goes straight down. It's on a surface. It's on a horizontal snow, so the snow is going to push up. We know that those two forces are canceling each other out again because it's not accelerating up or down. There is an acceleration here because it says the velocity of the bobsled changes. It's slowing down. So if we have the bobsled moving to the right, which is the way that I would imagine it going, so it's moving to the right, which way would a force have to act on it to make it slow down? It's going to act in the leftward direction. And looking at our choices here, that's going to be some sort of friction. It's going to be kinetic friction. Why is it kinetic friction? Because what's happening to the sled? It's moving. So FFK, force of friction, kinetic, that is the proper answer for that one. So we got these three things: gravity, normal force, kinetic friction. That's it. Okay, so I'm going to stop there right at 40 minutes. Sorry, it's a little long, but we got through a lot of good information that you're going to use. The next couple videos are devoted to problem solving. Have a good one.